Today we're going to go over the Chapter 11 review questions. This is the chapter that covers acids and bases. So as normal with review questions, I am not going to be going over the first question because it's the question that has all the key terms and definitions, and you can look that up in the book yourself. But question number 2 and question number 3 we're going to do at the same time, because those are 2 questions that ask us what are the 3 key things that you learned about acids. And then the next one asks you what are the key 3 things that you've learned about bases in this chapter. And so I had all that still written down on a piece of paper, and I hope you can see it. But if you'll remember about acids, these taste sour. This is your lemon juice or your orange juice. You shouldn't taste your chemistry lab chemicals, but if you have a beverage or a fruit and it's very sour, it's probably an acid. They are also covalent electrolytes. They donate a hydrogen in water. They actually can conduct electricity. And they also turn blue litmus paper red. And so those are your 3 for acid. So your 3 for a base is that they taste bitter. They feel slippery when wet. So you like anything on the soap, anything soapy, you wash your hands, your laundry, your dishes, that feels slippery in your fingers. That is a base. And then the next one for a base is it turns red litmus paper blue. So I like to try to say bases turn blue. Question number 4, I want you to name 2 acid-base indicators that they've talked about in the chapter. And so the first one is litmus paper, because we just talked about it in our properties of acids and bases. This comes from lichens, and it can change colors based on if something's an acid or a base. And then the second thing that we talked about are anthocyanins. And so this is just a red or purple cabbage, and anthocyanins are compounds that change colors based on their pH. So hopefully in lab you took some cabbage, some of the leaves off, and you boiled it to make a juice that changed colors based on its pH. So number 5 asks if lye is an acid or a base. And so lye is spelled L-Y-E, and this is actually composed of NaOH. You did this in your titration lab where you took acetic acid or vinegar and you titrated it with lye. And so since it ends in an OH, I know that this OH is going to accept a hydrogen, and so therefore it is a base. Question number 6 is a fill in the blank. And the first blank says blank are found in things that we eat or drink. And if you remember from lab, a lot of the things that you tested that you eat or drink are actually acids. And then the second blank is what is found in household cleaning products. And we've talked before that bases feel slippery when they're wet, and those are soaps. So your cleaning products are usually bases. For question number 7, it actually gives you 3 equations, and it wants you to, in each equation, identify the acid and the base. And so for the first one, we have C5H5N. And I just want to see what's happening to that product. And if I notice, it goes from having 5 hydrogens to 6 hydrogens. And so this compound is actually accepting a hydrogen, and so that makes it the base. The other product we have is water. Water can act as an acid or a base, so we have to see what it's doing. And it's going from having 2 hydrogens to just 1 hydrogen. It's donating it, so it's the acid. So number B, or letter B, we also have water as a product, and we have another compound called C3H6O2. So if I look and see what's happening to the hydrogen here, it's going from having 6 hydrogens to 5 hydrogens. So it's giving a hydrogen away, and that makes it the acid. Where water is going from having 2 hydrogens to 3 hydrogens. Water is actually gaining a hydrogen here, and so water is the base. So these are 2 equations, both using water. Just one water is the acid, and one water is the base. So for letter C, we don't have water as a product. We have HCN plus pH 3. So let's just look and see what happens to this hydrogen here. And you'll notice that HCN goes to being just CN negative, so it's losing the hydrogen. And so if it's donating or giving away a hydrogen, it's the acid. And pH 3 is going to be pH 4, so it's adding a hydrogen or accepting it, and it is the base. Question number 8 wants you to give an example of an amphoteric chemical. And an amphoteric chemical is a chemical that can act as an acid or a base. Now, there are many of these that you will learn if you continue your education in chemistry, but the main one that we talk about in this chapter is water, as I've erased the board, but it was on, if you'll go back and look at number 7, problem A and B. Those are both examples of water, one acting as a base and one as an acid. So the main amphoteric chemical that you need to know is water. So number 9 of this chapter review gives you a list of chemicals, and it wants you to say if it's an acid or a base. And so just a quick refresher, if I am looking for an acid, I am usually looking for something with a hydrogen in the beginning, with a hydrogen in the beginning that it can give away. If I'm looking for a base, I'm frequently looking for a hydroxide or an OH compound. Now, the first one they give me is a little tricky because it does not have a hydrogen in the beginning and it does not have an OH at the end. But we do see this compound very frequently throughout the chapter, though, and every time we see it, it acts as a base. So I would just try to remember this compound as a base or write it down on your note card for the test. Now, this one's easy to figure out because it has that nice H in the beginning, and so that's a super easy clue that it's an acid. And the same also happens for the next compound. If I see this hydrogen in the beginning, I know I have an acid. So down here with lithium hydroxide, there's no hydrogen in the beginning, but there is an OH at the end, which is a good hint that it is a base. And the same for the last one, for zinc hydroxide. It ends in an OH, and so therefore it is also a base. So question number 10 says that you were told by a chemist that this compound, which is citric acid, is a polyprotic acid, which means it can donate more than one hydrogen. And let's say you're told it can donate 3 hydrogens. How can we rewrite this formula so that it looks from the formula like an acid that can donate 3 hydrogens? And so those formulas of acids all have a hydrogen in the beginning. And so for this one, since it tells me it'll donate 3, I'm going to pull 3 of those hydrogens out and put them in the beginning. So then I still have a C6. Now my hydrogen back here is going to become a 5 because I only want a total of 8, and 5 plus 3 is 8, and then O7. So this is how you can write the formula for citric acid so that you can easily see that there's 3 hydrogens in it that can be donated. So number 11 tells us that hydrogen bromide is a strong enough acid that when it reacts with water, it makes water act as a base. That's kind of an important fact for this problem, because if you'll remember, water is amphoteric and it can act as an acid or a base. So they specifically tell you that in this equation, it's your base. And we're going to finish writing the equation. So if HBr is the acid, I know that it's giving away a hydrogen, and I know that the base, is accepting it. When my HBr gives away a hydrogen, the Br actually becomes an ion with a negative charge or a negative balance on it, and so then the water gains a hydrogen, and this hydronium ion becomes a positive, because remember, a hydrogen takes with it its positive charge. Number 12 wants to give you lots of practice in writing and then balancing these equations. Don't forget both parts of that. So let's start with part A, where we have sulfuric acid and we're actually reacting it with that base. Remember, this is the one you're supposed to learn is a base. And so what's going to happen is sulfuric acid has 2 hydrogens to give away to the base. So it becomes SO4, and its charge is 2 minus, and you actually may remember that from your polyatomic ions. Now, it can't give 2 hydrogens to just one NH3. One NH3 can actually only hold 1 more hydrogen to it, because nitrogen can only make 4 bonds. And so you end up with an NH4 plus ion. This is not balanced because that would be too nice of them, so let's balance it. So when you're balancing it, if you'll keep the sulfate as one ion, that'll make this a lot easier. So in this one we have like one sulfate and then one sulfate. So we also have one nitrogen and one nitrogen, but what's not balanced are the hydrogens. So here we have 1, 2, 3, 4, so we have 5 hydrogens on this side, and we have 4 hydrogens on that side. So how can we adjust the hydrogens? Well, let's do this. Let's put a 2 here, because if I put a 2 there, I now have 8 hydrogens on that side, and I can actually make these equal 8. Because if you'll realize there's 2 here, so this needs to be 6. So if I put a 2 here, this 2 times 3 is 6, 7, 8. So now I have 8 hydrogens on both sides, and it also balanced out the nitrogens because you have 2 nitrogens on both sides. So for letter B, you're taking HF, which is your acid, and you're reacting it with aluminum hydroxide. And so it's very easy to figure out what's the acid and the base because the acid has an H in the beginning and the base has an OH on it. So let's combine them and let's see what we get. So if you'll remember, in these types of reactions, you're actually producing a salt plus water. And so water's the easy product. And then when I go to take what's left over, after I pull the hydrogens and the hydroxide out, I'm left with a fluoride and an aluminum. So I'm gonna have to make a compound for that. Now, if you'll remember, aluminum has a charge of 3 plus, and fluorine has a charge of 1 negative. So you're gonna have to do your crisscross method to balance out your charges. And you have aluminum fluoride. Now, it is definitely not balanced because I have 3 fluorides and 3 fluorides. So let's balance it. So now my fluorides are balanced. Let's check our aluminums are balanced 1 to 1. Now I'm gonna go back and I'm gonna check my hydrogens and my oxygens. So I have here 3 oxygens, and on here I only have 1 oxygen. And so let's add a 3 here, and then check your hydrogens. So you have 6 hydrogens here, 3 hydrogens here, but you also have 3 here. So these 3 plus 3 makes 6, so we're even, it's balanced. So let's move on to the next problem. We have some phosphoric acid and we're gonna add it to calcium hydroxide. And so this is another one where I can easily see that this is my acid and this is my base, and when I have a hydrogen and an OH, those add together to make water. And what's left over is the phosphate and the calcium. So I'm gonna write calcium first because it's the cation or the positive charge. And phosphate last. If you'll remember from your periodic table, calcium is in the second row, so it has a charge of 2 plus, and phosphate is one of those polyatomic ions that you should have known, and so crisscross the charges. And you get Ca3PO42. Make sure that phosphate group stays in parentheses. So let's go ahead and balance it. If you want a challenge, go ahead and pause it and come back and check your work to my work. First, I'm gonna see easily that the calciums are not balanced. Remember, water last. So I've got 1 calcium and 3. So I'm gonna put a 3 here. I also can tell that the phosphates, I've got 2 phosphates and 1 phosphate. So I'm gonna add a 2 here. And once I've done everything but the hydrogens and the oxygens, then I will go back and balance those out. So here we have 4 times 2 is 8 oxygens plus 2 times 3 is 6. So 8 plus 6, so we actually have 14 oxygens over here. And over here we have 4 times 2, which is 8. So we need 6 oxygens here. So let's just see if we put a 6 here, if it balances. So with that 6 here, not only do I have balanced oxygens, but I have 12 hydrogens. So over here, I've got 3 times 2 for my hydrogens is 6, and also 3 times 2 is 6. So we have 6 hydrogens and 6 hydrogens. So that one is now balanced. So for letter D, we have another acid with a hydrogen in the front and another base with a hydroxide. And so those make water plus your salt. So first make your water and then combine your chromate, if you don't remember your polyatomic ions, with your magnesium. Magnesium is your cation, so it's gonna go first. And if you remember, magnesium is a 2+ and chromate is a 2-. So that formula is balanced out. We do not have to crisscross our charges. So now let's balance it, saving water for the last. You could start with magnesium or chromate. It doesn't really matter which one. Magnesium, I have 1, and chromate, I have 1. Magnesium in the products you have, in the reactants you have 1, and in the products. And the same for chromate. I actually have 1 chromate here and 1 chromate there. So let's check out the hydrogens and oxygens. Now, since I'm keeping chromate the same, I'm not gonna count its oxygens. So for this one, I have 2 hydrogens plus 2, so I totally have 4. And in the products, I only have 2, so I'm gonna need a 2 here. I also, for my oxygens, remember, I'm not gonna count those because I'm keeping that polyatomic ion together, but I have 2 oxygens. And then over here, I have 2 now. So that one was actually pretty easy to balance. Question number 13 gives me 5 pHs, and it gives me a list of 5 different scenarios or solutions, and it wants me to match the pH to the solution. So the first one, it says a solution of NaCl and water. Well, NaCl is just table salt, and if you'll notice, it does not have a hydrogen. It is not a base, it doesn't have a hydroxide, and so it actually is neither an acid nor a base, and so it's neutral. And so it would be 7, actually gives us a decimal, so 7.0. And then solution B, it says a concentrated solution of a strong acid. So if you'll remember, acids go from 0 to 6, so acids are gonna be, a concentrated strong acid is gonna be a low number. And so it's going to be this one. Number C tells us this is sour, but pleasant to drink. Acids taste sour, so I'm going to look for an acid less than 7, and this would be 4.5. This would not be the 0.1, because 0.1 is way too acidic for you to be drinking. D tells us glass cleaner that we buy at the supermarkets. I've got 2 left. I have 9, which is basic, and I have 14, which is basic. Now, 14 is very basic. Like, you're probably not gonna find anything of that pH at your supermarket or grocery store. And so an E also tells me this one is very caustic. So I know that this one's gonna be 14, and then like a regular glass cleaner, I think like Windex, the blue stuff you spray on your windows, is gonna be 9. Question number 14 is asking me what volume of a 3.17 molar solution of sulfuric acid would be required to neutralize 750 milliliters of a solution of NaOH. And so before I can even do this, I actually first have to write the balanced chemical equation. So let's go ahead and start with that. We're taking H2SO4 and I'm adding it to NaOH. Now hopefully you know that these hydrogens in the beginning tell you it's an acid, and that this OH tells you that this is the base. The hydrogen and the hydroxides are going to be making water. And what's left over is going to be combining into a compound. Na has a charge of +1, and SO4 or 1+ has a charge of 2-, so you're going to have to swap your charges to make sure that that compound charges balance out. So now we have to balance the equation. So I would leave water for last. Go ahead and start with either SO4, which it looks like we just have 1 and 1. So then the next thing I would check would be my sodiums, and we actually have 2 here, and we have 1 here. So I would put a 2 in front of this to tell me that there's 2 there. And now check your hydrogens and your oxygens. So since I'm leaving sulfate as 1 as I'm balancing it, I'm not going to add those oxygens, but I've got 2 oxygens here and 2 hydrogens here. I also have 2 hydrogens here. So if I take these 2 hydrogens and these 2, I have 4. So I need to put a 2 in front of the water. That will then give me 2 oxygens and these 2 oxygens. So now that it's balanced, I'm going to try and figure out just what I'm even doing in this equation. For me, the hardest part is sometimes just telling what are the steps to do. So they give me a lot of information. They tell me that I have 3.17 of this, molars, 3.17 moles. I'm actually looking for the volume. And then I know my information of this, of my sodium hydroxide. So it's 2.12. And I know the volume. So I have a molarity here and a volume, and I have a molarity here, but I'm trying to find a volume. So the first step that I tell you guys all the time is go to moles. So what you're gonna do is you're gonna calculate moles of NaOH. From moles of NaOH, you can then calculate moles of H2SO4. From moles of H2SO4, you can then calculate the volume of H2SO4. So this is 3 steps to this problem. So let's first start out here and calculate moles of NaOH. For 750 milliliters, I'm actually gonna put it in liters because molarity is in moles per liter. So go ahead and move your decimal. And I'm gonna do, so this is liters. So I want liters on the bottom, and this is moles. And this is of NaOH. Now liters cancels out, and I will be left with my answer in moles of NaOH. Now, if you'll pay attention, it's gonna have 1, 2, 3, 1, 2, 3, 3 significant figures in this answer. And you get 1.59 moles of NaOH when you do 0.75 times 2.12. So now that I'm in moles of NaOH, I'm gonna go to this step where I have to take moles of this and calculate moles of this. So this is where we use the coefficients from your balanced chemical equation. So I'm gonna put NaOH on the bottom. And what I'm going to on the top now, H2SO4 has a 1 in front of it, and NaOH has a 2 in front of it. So I put the NaOH, the 2 on the bottom, so that NaOH cancels out, and you're gonna put in your calculator 1.59 divided by 2. So when you do that, you should get 0.795 moles of H2SO4. And so now you can actually use your molarity of this. So we know molarity and we know moles, but we're looking for the volume. So I'm going to start with what I have. And if you'll remember, molarity is moles over liters. Since I'm looking for liters, I'm actually going to put liters on top and moles on the bottom. So I'm kind of flip that one, 3.17. Moles cancels out, and I get 0.251 liters of H2SO4. So for this step, you would take 0.795 and divide it by 3.17. So just a recap of what we did is we knew a lot of information for sodium hydroxide. So I was able to use the molarity and the volume to calculate the moles of this. Then I was able to use my balanced chemical equation to go from moles of this to moles of the acid. Once I had the moles of the acid calculated, you are then able to use the molarity to calculate the volume of the acid. I'm not going to write out all of question number 15. It just takes up too much space. So I'm just going to pull out the information that we need, and we're going to write the equation from it. But it says a student needs to neutralize 1.5 liters of 5.6 molarity of HCl solution. And then it tells me we're adding aluminum hydroxide, and it wants to know how much aluminum hydroxide. So I know my two reactants are HCl, or hydrochloric acid. So I know my reactants are hydrochloric acid and aluminum hydroxide, and I have a hydrogen and I have a hydroxide, so I'm gonna make water and aluminum chloride. Now aluminum has a charge of 3 positive and chloride of 1 negative. So if I cross those charges, I end up with a 3. So aluminum chloride. You have to go back and balance this equation, leave the waters for the end. So we have 1 aluminum and 1 aluminum, and we have 3 chlorines, so we need a 3. We need a 3 here. And let's look at what that does to our hydrogens and our oxygens. So we have 3 hydrogens, and here we have 3. So we have a total of 6 hydrogens. So I'm gonna put a 3 here. And on this side, I now have 3 oxygens, and all I have are 3 oxygens there. So it's balanced out. So now I'm gonna take the information that they give me in the problem, and I am gonna put it above it like I always do, so then we can figure out what we're doing. So they give you a little bit of information on this problem. They tell me I have 1.5 liters of a 5.6 molar solution of HCl, and it wants to know how many grams of aluminum hydroxide do I have to produce. Well, the first step I'm gonna do is I'm gonna figure out how many moles of HCl I have. They give you 1.5 and it's already in liters. So I'm gonna use the molarity, which is moles over liters. Liters will cancel out, and you're left with 8.4 moles of HCl. So you're just gonna do 1.5 times 5.6, getting messy today. And now once I'm in moles of HCl, I'm not looking for any information on HCl. The problem is asking for the aluminum hydroxide. So I'm gonna use my balanced chemical equation to go from HCl to aluminum hydroxide. So I'm gonna put HCl on the bottom. And aluminum hydroxide on the top. And so I actually have 3 of HCl's and 1 of aluminum hydroxide. So you're gonna put into your calculator 8.4 divided by 3. You get 2.8 moles of aluminum hydroxide. Now the question doesn't ask for moles, that would be way too easy. They want you to give it to you in grams, but you should be really good at converting from moles to grams. And so you're gonna take your 2.8, and we're going to grams, and we're canceling moles out. And so if you'll remember, this is your molar mass from the periodic table, and it's been a minute since we've had to add these up. So go ahead and add up an aluminum and 3 hydroxides. And when you add up your molar mass from your periodic table, you get 78.01. And so if you take 2.8 and you multiply it by 78.01, your moles cancel out and your units are grams. And so you're gonna end up with a result of 220 grams of aluminum hydroxide. So just as a recap as to what we did, they gave us a lot of information for hydrochloric acid, and they were asking us for how many grams of aluminum hydroxide to neutralize it. So we first calculated moles of hydrochloric acid, then we used our equation to go from moles of the acid to moles of the base, and then from moles to grams, which is basic stoichiometry that you've been doing. Number 6 gives us a statement, and it asks you what is wrong with the statement. And so the statement is the endpoint of a titration occurs when the number of moles of an acid equals the number of moles of a base. And so the problem with that is that the endpoint actually doesn't always occur when the moles are equal to each other. It just depends on the compound, but it does occur when there's enough moles to neutralize, like enough moles of the acid to neutralize the moles of the base. So question number 17 tells me we're using an indicator called bromothymol blue. You probably actually didn't use this in class, but just in case if you did, you will notice that from 0 to 6.8, it has a color of yellow. And if it is from 6.9 to 8.2, it is green. And then when it goes from 8.3 to 14, it is blue. And so the question then tells me that we're using it for an acid-base titration, and we're starting within our flask, we have an acid, and we're gonna be adding the base to the acid. And it wants to know what is the original color in the flask, and then what will be the color change that I'm looking for to tell when I have an end point. Well, so since the original, it's an acid, I'm going to be looking for which one of these pHs is an acid. And acids are from 0 to 4 or 0 to 6. And so, or 0 to, so the acid is this one, and it's yellow. And as you add the base to it to neutralize it, you're going to be looking for it to be in the green range, because this is the neutral range. If you get it all the way to the blue, you've actually gone past the end point. So for question number 18, I'm not going to write the whole question down, but it basically is a titration equation. It says you have 15 milliliters of a solution of H2CrO4, and since that has the H in the beginning, that's your acid, but we don't know its concentration or its molarity. And we're titrating it with a known concentration of potassium hydroxide. And it's wanting to ask us how much we have to add to hit the end point. So the first part of this, as is always, is going to be to write the equation out. These are the reactants that they tell you. This acid and base, I have a hydrogen and a hydroxide, so I know my products are going to be water. And then my other product is going to be the potassium and the chromate. The potassium is in the first column, so it's a charge of +1, and chromate is a 2 negative, and so actually you need to crisscross those charges and have 2 potassiums. Now the next step to this equation is to balance it, so balance the water last, and so let's check. You can either do the chromate or you could do the potassium first. It doesn't really matter which one. But let's look at potassium because it's pretty easy to see. We have 1 potassium here and we have 2 there. So I need to put a 2 here. So now let's look at chromate. We have 1 and 1. So now we have hydrogens and oxygens that are left, and that's going to be messing with the water. So in this equation, I have 2 hydrogens plus the 1, so I have 3 hydrogens. So as I'm counting up oxygens, I'm not going to use the oxygens of the chromate. So I'm just going to say here I have 2 oxygens here and I have 1 oxygen here. So I need to make sure I get at least my 2 oxygens there. Let's count now. I have 2 oxygens and I have 4 hydrogens. So I have 2 oxygens and I actually have 4 hydrogens. So now it's balanced. So the information that they give you in the problem is they tell you that you have 150 milliliters of of H2CrO4, and they also tell you that you used 1.16 molarity solution of the potassium hydroxide, and it actually took 13.1 milliliters to reach your end point. And so now the question is asking me, what is the concentration of this compound? And so, just like we've done in past problems, if you're stuck, I would say go to moles. I'm going to go to moles of potassium hydroxide because I have enough information to do that. Then you're going to go from moles of this and use your equation to go to moles of this. From moles of this, we can then use the moles of this and the liters of this to calculate the concentration. The first step is to figure out the moles of the potassium hydroxide. So I've got 13.1. And it doesn't matter which of these you start with. You could work it with either way. And I'm actually going to make it liters because molarity is moles per liter. So 1, 2, and move it over here. 3, getting messy today. Liters, and I'm going to multiply it by 1.16 moles over 1 liter. So what's going to happen is liters are going to cancel out, and you do the multiplication just straight through your calculator, 0.013 times 1.16, and you get 0.0152 moles, and this is of the KOH. So now once I have moles of the KOH, I'm going to use my balanced chemical equation to calculate moles of the acid. And the coefficients are 1 and 2. So KOH goes on the bottom, so it cancels out this number, and you divide it by 2. And I'm running out of space, so I'm going to put it down here. All right, so what I just did is I basically took my moles, my molarity, and my volume of KOH, and I was able to figure out the moles of KOH. And I used the coefficients from the balanced chemical equation, which is a 1 and a 2, to cancel out KOH and convert to moles of the acid. I ran out of space. I'm starting it down here. So now that I'm in moles of the acid, the question is actually asking me for the molarity of this. So to find molarity, I need moles and I need liters. Well, I actually have moles and I have milliliters, so I can actually make liters. 0.150 liters. So you're just going to do the division in your calculator and you'll get the molarity. And when you do the division, you get 0.507 molar. Question number 19 gives you two cleaning solutions. It gives you Lime Away, which is a type of toilet bowl cleaner that you can buy, and it has a 10% HCl concentration, and a muriatic acid that you can find at your big box hardware stores like Lowe's or Home Depot, and it has a 30% of HCl acid. And so the question wants you to tell them which one is better for getting rid of lime stains and which one is safer. So lime is a calcium buildup that you get in your water. Depending on where you live, you may get a lot of it, and you sometimes can see it on your faucets. It's kind of green or white, chalky looking buildup. And so the one that would be better at getting rid of it is actually the muriatic acid, because it is a lot more concentrated. However, this one will be safer to use. Question number 20 is a dilution problem, and it tells you have concentrated acetic acid, and we actually have a 17.4 molar solution, and this is the acid that's found in just regular old vinegar that you buy at your grocery store. And then it tells me that we have 250 milliliters of a 3.5 molar solution. It wants to know how I would make this solution based on all this information. And so this is a problem that I work different than in the book. If you want to work it the way they work it in the book, that's just fine. But I really like for these problems to use M1, V1, M2, V2. So the M is molarity and the V is volume. And so this is basically the first scenario, and this is going to be the second scenario. So for the molarity of the first one, we have just 3.5, hearing my dog, and it's a molarity, and we're going to multiply that by the volume. We can keep it in milliliters if the whole thing stays in milliliters. So got 250 milliliters, and the second one, I've got a molarity of 17.4. And I'm wanting to know how much water I'm going to need to dilute it to. If I multiply these together, I get 875. Then I'm going to divide by 17.4 so that I get volume alone. And so when I do that, I get V2, which is equal to, I get 50 milliliters. Now your book says 0.05 liters, which is the same thing. So if you wanted to do that, but what this basically means is that in order to take this 17.4 molarity solution and dilute it down to 3.5 molarity, and I want a total volume at the end of 250 milliliters. So what I would have to do is I would take 0.05 liters or 50 milliliters of this solution and dilute it to 250 milliliters, and I would have the concentration that I was wanting. For number 20, I'm going to work it a second way, and I'll work it the way that the book teaches it, just so that I don't confuse any of you if you're really just that's the way you do it. And so the first thing I would do is I would figure out how many moles I would need to make the solution of my constant, of how many moles of it I would need. And so I have 3.5 molar. Since 3.5 molar is moles over liters, and I want liters to cancel out, tells me I have 0.25 liters. And so I would multiply 3.5 times 0.25, and that would give me the moles of the acetic acid. Now for the new compound that I'm forming, I have a molarity of 17.4. And I know it equals the moles over the liters. And I don't know what the liters are. I was trying to make a question mark there. And so I'm just going to solve this problem for liters. So I would multiply both sides by liters, and you would end up with the liters over here. Then divide by 17.4. And your liters would get 0.05 liters, which is the same that I just did. There's just two ways to do it. For the last one, it's another dilution problem. It says that a chemist makes 50 milliliters of NaCl, and it's a 2, and there's a decimal there, 0.5 molar molarity solution, and they want to take this solution of 2.5 molars and they want to actually dilute it down to 1.75, and it's asking me what is the volume of this that I need to take. And so I'm going to use the M1 V1 M2 V2 because that's just my preference. So M1 2.5 times the volume. Since your book is doing it in liters, let's go ahead and put it in liters. So you've got 0.05 liters. And it is going to be equal to M2, so the molarity that I'm going to, which is 1.75. And I'm just looking for the volume of that. And so if I go through this and I do 2.5 times 0.05, I get 0.125 equals 1.75 volume, so I'm going to divide by 1.75 to get volume alone. And the volume that you get is 0.07 liters. We're making 0.07 liters or 700 milliliters. So you would need to take this amount of the original solution and add it until you get to 700 milliliters. And that would actually result you with that would dilute it down to a 1.75 molarity solution.